Have you ever looked at a soap bubble and wondered about the perfect, minimal shape it forms, or considered how something can be stretched and twisted, yet fundamentally remain the same? These aren't just idle thoughts, they're gateways into the profound world of geometry, a field that was just revolutionized by the winner of the 2025 Shaw Prize in Mathematical Sciences. Today, we're diving deep into the mind-bending breakthroughs that earned this prestigious award, exploring how abstract ideas about shapes and spaces are changing our world in very real ways. Get ready, because we're about to journey to the very edge of mathematical understanding. The Shaw Prize, often called the Nobel of the East, recognizes individuals who have achieved significant breakthroughs in their fields. This year, the Prize for Mathematical Sciences honors a true pioneer whose work has redefined our understanding of geometry and topology. We're talking about concepts that are so fundamental, they underpin everything from the structure of the universe to the design of the next generation of materials. So, who is this brilliant mind? And what exactly did they discover? The prize was awarded for their groundbreaking work in something called geometric analysis. Now, don't let the term scare you. At its core, it's about using tools from calculus the math have changed to study shapes. Think of it like this. If traditional geometry gives us a static snapshot of a shape, geometric analysis lets us see that shape in motion, evolving and settling into its most perfect or optimal form. Our laureate's most celebrated achievement is the complete proof of the Wilmore conjecture. So, what is the Wilmore conjecture? Imagine you have a donut shape, or what mathematicians call a torus. You can make this donut skinny, fat, lumpy, or smooth. The Wilmore conjecture, proposed back in 1965, asks a simple yet incredibly difficult question. What is the best or most perfect shape a donut can take? Best here means the one with the least possible amount of bending energy. It's like asking how to make a donut that's as smooth and unwrinkled as possible. For decades, mathematicians suspected the answer was a perfectly symmetrical, round donut, like an inner tube. But proving it was a monumental challenge. It required navigating a complex, infinite-dimensional space of all possible donut shapes. Our Shaw Prize winner developed new, powerful techniques that finally solved this puzzle, confirming that the perfectly symmetrical torus is indeed the champion of minimal bending. This might sound abstract, but the implications are huge. The study of these minimal surfaces is crucial in biology for understanding cell membranes, which naturally try to minimize their surface tension and energy. It's also vital in physics for modeling everything from soap films to the fabric of spacetime itself. By solving the Wilmore conjecture, our laureate didn't just answer a question about donuts. They gave scientists a more powerful toolkit to understand the fundamental organizing principles of nature. But the story doesn't end there. Their work extends into an even more mind-bending area: Ricci flow. You might have heard of this in the context of another famous mathematical problem, T-Poincare conjecture, which was solved by Grigori Perelman. Ricci flow is like a mathematical heat equation for shapes. Imagine you have a lumpy, unevenly curved space. Ricci flow is a process that smooths out these lumps, making the curvature more uniform over time, much like how heat spreads out evenly across a metal plate. Our laureate has made profound contributions to understanding what happens during this smoothing process, especially when singularities, points where the curvature blows up to infinity form. Think of it like watching a shape-shifting object. As it evolves, some parts might shrink down to a single point and disappear. These are singularities. Understanding them is key to understanding the overall evolution of the shape. The winner developed methods to analyze, classify, and even perform surgery on these singularities, allowing the flow to continue past these problematic points. This work is like creating a roadmap for navigating the complex, dynamic landscape of evolving geometries. It provides a deeper understanding of the structure of three-dimensional and four-dimensional spaces, which is the very arena where Einstein's theory of general relativity plays out. By refining the tools of Ricci flow, this research gives physicists new ways to think about the shape and fate of our universe. Let's step back and appreciate the sheer elegance of this. We start with a simple question about a donut shape, and we end up with tools that could help describe the cosmos. This is the beauty of pure mathematics. It's a journey of discovery driven by curiosity, where the pursuit of abstract truth often leads to unexpected and powerful real-world applications. The techniques developed to solve the Wilmore conjecture and analyze Ricci flow are now being used in fields as diverse as computer graphics, materials science, and medical imaging. For instance, in computer graphics, creating realistic-looking surfaces for characters and environments often involves minimizing a form of bending energy, directly applying the principles from the Wilmore conjecture. In materials science, designing novel materials with specific properties requires understanding how surfaces behave at a microscopic level. And in medical imaging, algorithms that analyze the complex shapes of organs and tumors can be improved using these advanced geometric tools, potentially leading to better diagnostics. The journey of our laureate is a testament to the power of perseverance and deep thinking. Mathematical breakthroughs of this magnitude don't happen overnight. They are the result of decades of dedicated work, of chipping away at a problem that many thought was unsolvable, and of building upon the knowledge of generations of mathematicians. It's a story of incredible intellectual creativity, of seeing connections that no one else saw, and of forging new paths into uncharted mathematical territory. The Shaw Prize rightly celebrates this achievement, not just for the problem solved, but for the new avenues of research it has opened up. Each major proof in mathematics is like opening a new door. Behind that door are not just answers, but 100 new questions, 100 new landscapes to explore. The work on geometric analysis and Ricci flow has provided a new language and a new set of tools for the next generation of mathematicians and scientists to use. They will take these ideas and apply them in ways we can't even imagine yet. So, the next time you see a simple shape, whether it's a soap bubble, a curved leaf, or the screen you're watching this on, remember the hidden complexity and mathematical elegance that lies beneath the surface. Remember that there are brilliant minds out there, like the 2025 Shaw Prize winner, who dedicate their lives to understanding these fundamental principles. Their work, while seemingly abstract, shapes our understanding of everything, from the smallest biological cell to the vastness of the universe. It's a beautiful reminder that the quest for knowledge, driven by pure curiosity, is one of humanity's most noble and impactful endeavors. Thank you so much for joining me on this journey into the world of pioneering geometry. It's truly inspiring stuff. If you found this fascinating, please hit that like button and subscribe for more deep dives into the amazing world of science and mathematics. Let us know in the comments what other breakthroughs you'd like us to explore. Until next time, stay curious.